Space is not what you think it is. We imagine it as empty, static. But it moves. It does not sit still. It stretches, expands, and it can do something that seems impossible. Space can stretch faster than light. Nothing can move through space faster than light. That rule holds. But space itself is not bound by it. During the universe's first moments, space expanded explosively. Regions pulled apart faster than light could travel between them. This was not motion through space. It was the expansion of space itself. And it continues today. Some regions of the universe are expanding away forever. Distant galaxies recede not because they race through space, but because the space between us and them stretches. If a galaxy is far enough away, that stretching makes it recede faster than light. Its light will never reach us. Not in 1 billion years. Not in infinite time. These galaxies have already passed beyond a cosmic horizon, slipping away, unreachable. The universe is not just growing, it is quietly letting go. This expansion creates a strange paradox. The observable universe is 93 billion light-years across, but the universe is only 13.8 billion years old. How can we see something farther than light has had time to travel? The answer lies in expansion. Light from distant galaxies began its journey long ago, but while it traveled, space itself expanded. The distance grew. A galaxy that emitted light 13 billion years ago is no longer where it was. Space has carried it farther away. Today, that galaxy sits 46 billion light-years from us, its light finally arriving after an impossibly long journey through stretching space. And the universe contains more than distance. It contains numbers beyond comprehension. There are more stars in the universe than grains of sand on all of Earth's beaches. Every shoreline, every desert. Estimates suggest there are roughly 10,000 stars for every grain of sand. Hundreds of billions of galaxies, each containing hundreds of billions of stars. The total number exceeds human intuition. We see only a fraction of this vast population. The edge of the observable universe is not the edge of the universe. It is simply the limit of what light has had time to reach us. Beyond that edge, more galaxies exist, more stars, more planets. But their light has not yet arrived. And because expansion accelerates, some never will. This raises a profound question. Does the universe have an edge at all? Or does it continue forever? The universe may be infinite. Current observations suggest space goes on without boundary. No center, no edge. Just more galaxies, more stars, more space. If true, it means most of the universe will always be beyond our reach. We will never see all of it, no matter how far we look, no matter how long we wait. An infinite universe does not mean infinite possibilities, but it does mean endlessness. A quiet vastness stretching without conclusion. And within this vastness, something remarkable exists. You. You are made of stardust. The carbon in your body, the calcium in your bones, the iron in your blood, all were forged in stars. Stars that burned, exploded, scattered their remains across space. That material drifted, clumped, formed new stars, new planets, and eventually you. You are not separate from the cosmos. You are a moment of it made conscious. The universe has grown eyes, and through those eyes, it looks back at itself. Even as distances grow, even as galaxies slip beyond reach, you remain connected, made from the same material, shaped by the same forces. The forces that shape the universe create objects of incomprehensible density. A raindrop-sized piece of a neutron star would weigh more than Mount Everest. Neutron stars are the collapsed cores of massive stars, only about 20 kilometers wide, but their mass exceeds the sun's. The matter inside is crushed so tightly that a single teaspoon weighs billions of tons. Atoms are destroyed. Electrons and protons merge into neutrons, forming a kind of superfluid neutron soup. If you could hold a raindrop of this material, it would be heavier than any mountain on Earth. That kind of density defies everyday experience. Yet neutron stars are small compared to what else exists. The largest known stars could fit 5 billion suns inside. These hypergiant stars dwarf everything familiar. Stars like Stephenson 2-18 or UY Scuti, so vast that if placed at the center of our solar system, their surface would extend beyond Jupiter's orbit. Earth would be vaporized, Mars would be swallowed, even Jupiter would orbit inside the star itself. The scale is almost impossible to visualize. Yet these giants are diffuse. Their outer layers are thinner than laboratory vacuum. They shine with immense power, but low density. Fragile balloons of plasma held together by gravity. In contrast, black holes concentrate mass beyond measure. The largest known black hole has a mass of 66 billion suns. It sits at the center of a distant galaxy, TON 618. If our solar system approached this black hole, we would be pulled in from light years away. Its gravity reaches across distances that dwarf galaxies. The event horizon, the point of no return, would be larger than our entire solar system, hundreds of times wider than Pluto's orbit. These objects are quiet, invisible except for the light of matter falling in, but their influence shapes everything nearby. Entire galaxies orbit them. Mass is not the only extreme. Some stars spin up to 716 times per second. These are millisecond pulsars, neutron stars rotating faster than kitchen blenders. The entire star, a city-sized sphere of nuclear matter, completes hundreds of rotations every second. Its equator moves at a significant fraction of light speed. If it spun any faster, it would tear itself apart. Centrifugal force would overcome gravity. These objects emit beams of radiation from their magnetic poles. As they spin, the beams sweep across space like cosmic lighthouses, ticking with astonishing precision. Some are among the most accurate clocks in the universe, and their magnetic fields are beyond comprehension. Magnetars have magnetic fields trillions of times stronger than Earth's. A magnetar's field could erase credit card data from thousands of kilometers away. It could distort atomic structures, tear matter apart. These fields are temporary. They decay over time. But while they last, they produce flares and bursts of high-energy radiation. A single magnetar flare, even from across the galaxy, can be detected on Earth. No laboratory could create such intensity. They are among the most extreme objects in existence. Dense, silent, and wrapped in invisible force. Yet even these pale beside the largest structures. The Great Wall supercluster stretches 1.4 billion light-years. It is a vast collection of galaxies connected by gravity and dark matter. A filament in the cosmic web. If you could see it from the outside, it would look like a thread woven through space. Thousands of galaxies strung together. Each galaxy containing billions of stars. And the entire structure spans distances so large that light takes over 1 billion years to cross it. This is one of the largest known structures in the observable universe. A reminder that scale works in both directions, from the unimaginably dense to the impossibly vast. Among these extremes, black holes stand apart. They do not just concentrate mass, they warp reality itself. In 2019, humanity captured the shadow of a black hole. The Event Horizon Telescope released the first direct image, not of the black hole itself, which cannot be seen, but of its shadow. The image shows a glowing ring of hot gas swirling around a circular darkness. That darkness is the region from which no light escapes. The black hole at the center of galaxy M87, about 53 million light-years away. It took years of global collaboration, telescopes around the world acting as a single planet-sized lens. The result was more than a picture. It was proof. A glimpse of one of the most mysterious objects in existence. Black holes do not simply pull. They twist space and time into funnel-like structures. As you approach a black hole, space bends inward. Time slows. To an outside observer, time near the black hole appears to crawl. At the event horizon, it almost stops. This warping creates something like a funnel in the geometry of space. Narrow, steep, one way. Inside, all paths lead toward the center, the singularity. The closer you get, the more time and space seem to trade places. Inward becomes a direction in time, not space. You cannot go back. Time slows dramatically near a black hole. If you could orbit just outside the event horizon, minutes for you would mean years elsewhere. This is not fiction. It is gravitational time dilation, a real, measured effect. We have observed it in milder form with satellites. GPS systems must account for it. Around black holes, the effect becomes profound. They do not just trap light, they stretch time itself. And if you fell toward one, your body would not survive intact. Falling in causes spaghettification. The gravity at your feet would be vastly stronger than at your head. This tidal force would stretch you, pulling you longer and thinner, like dough being drawn into a thread. Your atoms would eventually be torn apart. It would happen long before you crossed the event horizon. Black holes are not static. They can move, spin, and interact. Black holes can collide and merge. When two orbit one another, they emit ripples in space-time. Gravitational waves. As energy leaks away, the black holes spiral inward, faster, closer, until they merge in a final, dramatic moment. Two invisible giants becoming one. These collisions do not make light, but they send out bursts of gravitational waves, waves that travel across the universe, and we can now detect them. LIGO detected ripples from black hole mergers billions of light-years away. The first signal was observed in 2015, a burst from more than 1 billion light-years distant. When the waves reached Earth, they stretched space by less than the width of a proton. Yet we caught them. LIGO acts like a cosmic ear, listening to the universe's deepest rumblings. But black holes hold deeper mysteries. The black hole information paradox remains unsolved. According to quantum mechanics, information cannot be destroyed. But black holes seem to violate this rule. When matter falls into a black hole, all information about it appears to vanish. Its quantum state, its history, gone beyond the event horizon. Yet Stephen Hawking showed black holes can evaporate over trillions of years. If the information fell in, where does it go when the black hole evaporates? Is it destroyed or somehow preserved? The paradox remains unresolved. Black holes challenge our understanding of time, information, and reality itself. Black holes are not anchored in place. They move, interact, and sometimes wander. Some black holes wander alone through space. Not all black holes live in the centers of galaxies. A black hole can be ejected from its birthplace by gravitational interactions, kicked out during a collision, flung away by the recoil of a merger. Once released, it becomes a rogue object. These wandering black holes move silently through interstellar or even intergalactic space. They emit no light unless they pass through gas or pull on nearby stars. But they are likely out there, drifting through darkness, unseen and unbound. They carry no orbit, no companion, no home. Just mass, motion, and deep gravity. The violence that creates them can also send them flying. Black holes can be kicked across galaxies after mergers. When two black holes merge, the event sends out gravitational waves. But those waves are not always symmetrical. If the merger sends more energy in one direction, it gives the new black hole a recoil. A gravitational kick strong enough to hurl it away at thousands of kilometers per second. Some black holes may be flung entirely out of their galaxies, doomed to drift through intergalactic space. Others settle into wide, wandering orbits. These kicked black holes are hard to spot, but astronomers believe they exist, silent travelers pushed by the memory of their own collision. Not all black holes announce their arrival with fireworks. Some massive stars collapse directly into black holes without exploding. We often imagine the death of a massive star as a violent supernova, a brilliant explosion lighting up the galaxy. But for the most massive stars, the end can be strangely quiet. Some stars are so heavy that when they run out of fuel, their cores collapse inward. Gravity wins so completely, so suddenly, that even the outer layers fall straight in. No explosion, no bright farewell, just a sudden disappearance. This process is called direct collapse. In one moment, a star is gone, replaced by a black hole. Silent, invisible, and crushingly dense. Astronomers have even observed stars that seem to vanish without a trace, as if the light simply blinked out. It is a reminder that not all cosmic endings are fireworks. Some are whispers into the dark. But black holes are not entirely silent forever. Black holes emit faint heat through Hawking radiation. According to quantum theory, black holes can radiate. It happens at the edge of the event horizon. Virtual particle pairs appear briefly from quantum fluctuations. Occasionally, one particle escapes while the other falls in. The escaping particle becomes real, a tiny bit of energy lost from the black hole. Over incredibly long timescales, this slow leakage can cause the black hole to shrink and eventually evaporate. For a sun-mass black hole, that would take more than 1 trillion years. The quietest kind of ending. Not an explosion, but a long, slow fade. Meanwhile, black holes can fling other objects away with tremendous force. Hypervelocity stars can be ejected at 3% the speed of light. Some stars pass too close to a black hole. If they approach in pairs, one may be captured while the other is flung away at incredible speed. These hypervelocity stars move fast enough to escape the Milky Way entirely. Refugees from a gravitational slingshot. Supermassive black holes can eject stars from galaxies. At galactic centers, where millions or billions of solar masses concentrate, interactions become extreme. Stars that wander too close can be accelerated to escape velocity and thrown out entirely. These ejected stars become intergalactic wanderers, lone travelers in the dark. Black holes are not passive. They pull, they push, they wander, they eject. Among the most dynamic and violent objects in the universe. Black holes are violent, but stars have their own strangeness. The first stars burned millions of times brighter than the sun. The very first stars were unlike anything we see today. Born from pure hydrogen and helium left after the Big Bang, these stars, called population 3 stars, likely formed with no metals at all, making them massive, hot, and short-lived. Some may have been hundreds of times the mass of the sun. They would have burned through their fuel quickly, shining millions of times brighter than our own star, then collapsing in spectacular explosions after just a few million years. None of these stars survive today, but their brief lives changed the universe. They created the first heavy elements, seeded galaxies with light, and set the stage for everything that followed. Their light is gone now, but their fingerprints remain. Some stars carry memories older than their homes. Some stars appear older than the galaxies they inhabit. Galaxies are not built all at once. They form over time, merging with smaller systems. That means some stars inside a galaxy can be older than the galaxy's current structure. They may have formed in earlier, smaller galaxies that later merged. These ancient stars often live in the outskirts or in globular clusters. Some are over 13 billion years old, nearly as old as the universe itself. They carry the chemical signature of a much younger cosmos, when there were fewer heavy elements and only the simplest atoms. These stars are like fossils. Stars can sing through astroseismology. There's no air in space, but stars still make sound. Deep vibrations travel through their interior gases like seismic waves. Scientists detect them by observing tiny changes in brightness or surface motion. Each star has its own internal frequencies, like a fingerprint. By listening to these vibrations, scientists can peer inside stars, a kind of cosmic echolocation. Our own star participates in this. The sun rings like a giant bell. Sound waves ripple through the plasma, bouncing between layers. These waves are low, slow, far below human hearing. But scientists can detect them through helioseismology. By observing how the sun rings, they can map what happens deep below the surface. A star orbits the Milky Way in reverse. Most stars orbit in the same direction, following the galaxy's rotation. But at least one known star moves in the opposite direction, retrograde. It may have been part of a smaller galaxy that merged with the Milky Way long ago. Dying stars pulse like heartbeats. Some stars fade slowly, pulsating during their final stages. These variable stars change in brightness over time. Gases expand and cool, then collapse and heat again. Some pulse every few days, others take months or years. Even in death, stars can keep time with a long, slow breath. Some white dwarfs are made mostly of carbon. Under immense pressure, that carbon may crystallize. Some stars become giant diamonds, about the size of Earth, but far heavier. They glow faintly with leftover heat for billions of years. And when massive stars do explode, their remnants linger. Supernova remnants expand for thousands of years. The shock wave from a supernova doesn't end with the flash. It expands outward for centuries, or even millennia, sweeping up gas, dust, and anything in its path. These expanding shells glow in many wavelengths, forming delicate filaments or turbulent clouds. The Crab Nebula is one such remnant, still spreading from a blast seen on Earth in 1054. Supernova remnants are the slow exhalations of dead stars, still unfolding long after the light has faded. Stars are strange, but the worlds around them are stranger still. Thousands of rogue planets drift through space without stars. Not all planets orbit stars. Some are completely unbound, floating alone through the galaxy. These rogue planets may have formed normally, then been ejected from their star systems by gravitational chaos. Others might have formed on their own, like failed stars. They are dark, cold, and nearly invisible unless they pass in front of background stars or glow faintly in infrared. Astronomers estimate there may be billions of them in the Milky Way, perhaps even more than the number of stars. Each one is a silent world, adrift in darkness, spinning alone in the vast spaces between. No sunrises, no sunsets, just endless night, broken only by distant starlight. And some planets have compositions that defy expectation. Some planets may be made almost entirely of diamond. In certain solar systems, the chemistry is very different from ours. If a planet forms with more carbon than oxygen and the pressures are high enough, something remarkable can happen. Astronomers have discovered at least one such candidate: a dense world orbiting a pulsar. Based on its mass, density, and composition, the entire planet may be a crystalline form of carbon, essentially a giant diamond. It would not sparkle, and it would not look like a jewel up close. But deep beneath the surface, immense carbon lattices could stretch for thousands of kilometers. These strange worlds are not common, but they remind us how diverse the universe can be. A planet made of rock, a planet made of gas, and sometimes a planet made of crystal. Even familiar planets behave in unexpected ways. A day on Venus is longer than a year on Venus. Venus rotates incredibly slowly. One full rotation takes about 243 Earth days. But Venus orbits the Sun in only 225 Earth days. This means a day on Venus, from sunrise to sunrise, lasts longer than its year. And Venus rotates backward. The Sun rises in the west and sets in the east. Uranus also defies convention. Uranus rotates on its side. Most planets spin with their axes roughly perpendicular to their orbits. But Uranus has an axial tilt of 98 degrees. It rolls along its orbit like a barrel. One pole faces the Sun for decades, then the other. This extreme tilt may have been caused by a massive collision early in the planet's history. Something struck Uranus hard enough to knock it over. Saturn holds its own oddities. Saturn's rings are only 100 to 400 million years old. This seems like a long time, but Saturn itself is over 4 billion years old. The rings are young compared to the planet. They may have formed from a shattered moon or a comet that wandered too close. Over time, the rings will continue to erode. Material falling into Saturn's atmosphere. In another 100 million years, they may be gone. Saturn also hosts a massive hexagon-shaped storm. At Saturn's north pole, there is a persistent storm in the shape of a perfect hexagon. Each side is roughly 15,000 kilometers long. The hexagon has been observed for decades and appears stable. It is formed by a jet stream, a high-speed river of wind in Saturn's upper atmosphere. The geometry arises from the interaction between wind speeds and planetary rotation. Similar patterns can be created in laboratory fluids, but seeing one on a planetary scale is extraordinary. Jupiter's Great Red Spot is shrinking. The Great Red Spot is a massive storm that has raged for at least hundreds of years. But observations show it is getting smaller. In the 1800s, it could fit 3 Earths across. Now, barely 1. No one knows why it is shrinking, or whether it will disappear entirely. Some planetary features are temporary. Even in a system as old as ours, change continues. Change continues across the universe, carried to us by light. The oldest light comes from 380,000 years after the Big Bang. Before that moment, the universe was a glowing fog, so hot and dense that light could not travel far without scattering. But as it expanded and cooled, it reached a turning point. Atoms formed, the fog cleared, and light was suddenly free to move. That ancient light is the cosmic microwave background. We can still detect it today. It is the oldest direct signal in the universe, not from stars or galaxies, but from the universe itself, when it was just becoming transparent. The photons we observe now have been traveling for more than 13 billion years, stretched by expansion into long, cool microwaves. But we can see even farther back in another sense. We see galaxies from only 200 million years after the universe formed. Using the James Webb Space Telescope, astronomers identified light from a galaxy that existed just 200 million years after the Big Bang. That light has been traveling toward us for more than 13.5 billion years. The galaxy itself is small, faint, and primitive, but it holds clues to how the first structures formed. Observing it is like looking through a narrow window into a world we were never meant to see. The universe in its earliest chapters, when darkness was just beginning to give way to stars. Andromeda is visible to the naked eye from 2.5 million light-years away. On clear, dark nights, it appears as a soft, hazy oval in the sky. The light began its journey long before humans evolved. You can see an entire galaxy with no telescope, just your eyes and the sky. Some galaxy light is older than Earth itself. Light from galaxies billions of light-years away began its journey before Earth existed, before the Sun formed, before our solar system began to take shape. The stars we see in those galaxies may be long gone, but their light remains. Gravitational lensing lets us see one galaxy from multiple directions. In regions where gravity is strong, space-time curves and bends the path of light. We can see multiple versions of the same distant galaxy from different angles. These appear as arcs, smudges, or complete rings, different paths light has taken through warped space-time. Even a single planet can bend light. A single planet can bend light through microlensing. If a planet passes directly between a distant star and Earth, it can act as a tiny gravitational lens, magnifying and distorting the starlight. This effect is subtle and rare, but powerful enough to reveal planets we could never see otherwise, even in other galaxies. A flicker in the light, a gentle curve in the brightness, and suddenly, a world is revealed. When the alignment is perfect, something beautiful happens. Einstein rings form perfect circles of bent light. If the mass of a foreground galaxy bends light from something farther away, and the alignment is just right, the result is a perfect circle of distorted light. These are called Einstein rings. They are rare but beautiful, glowing loops suspended in space, formed not by motion, but by perspective and gravity. Natural lenses created by the shape of space itself. And some of what we see no longer exists. James Webb sees galaxies that no longer exist. The James Webb Space Telescope looks farther than ever before, and in doing so, it looks further back in time. Some of the galaxies Webb observes may no longer exist in the form we see them. They may have merged, faded, or changed entirely. But their light is still arriving. A snapshot frozen in time, still crossing space long after the source has changed. Telescopes do not show us what is out there now. They show us what was at different moments across the history of the universe. Every deep-field image is also a time machine, a gallery of vanished light. What we see is only a fragment of what exists. Dark matter passes through your body constantly. As you lie still, dark matter flows silently around you. It is not some invisible mist. It is a form of matter that does not interact with light, does not reflect, emit, or absorb it. But it has mass and responds to gravity. Our galaxy is surrounded by a vast halo of dark matter. As Earth moves through this halo, trillions of dark matter particles are thought to pass through every square centimeter of your body each second. They do not collide with your atoms. They do not leave a trace. But they are there, ghost-like, ever-present, and essential. Without dark matter, galaxies would not hold together. Cosmic structures would not form. The universe would be very different. And this invisible substance dominates everything. Dark matter makes up roughly 27% of the universe. Dark energy makes up roughly 68%. Normal matter is only about 5%. Stars, planets, galaxies, gas, dust, all of it combined, everything humanity has ever observed directly, amounts to just a sliver of the total. The rest is invisible. And dark energy is the most mysterious of all. Dark energy is accelerating cosmic expansion. The universe is not just expanding, it is expanding faster over time. Observations of distant supernovae revealed this in the late 1990s. Galaxies are moving apart at an increasing rate. Something is pushing space to grow. That something is dark energy. Unlike normal matter, or even dark Dark energy does not clump. It is spread evenly throughout space, and as space expands, dark energy does not dilute. It remains constant. This means the more space there is, the more dark energy there is, driving expansion faster and faster. A runaway process with no end in sight. Yet, despite its dominance, we know almost nothing about it. We still do not know what dark energy is. It may be a property of space itself, a kind of vacuum energy. Or it could be something more exotic, a new field, a fundamental force we have not yet understood. All we know is that it exists, that it pushes, and that it controls the fate of the universe. But its nature remains one of the deepest mysteries in cosmology. Meanwhile, the invisible dark matter shapes everything we see. Galaxies follow invisible dark matter filaments. Over billions of years, dark matter formed enormous filaments stretching across space. Galaxies tend to form and move along these filaments like beads on a string. We cannot see the filaments directly, but we can infer them by observing how galaxies cluster and how light bends as it passes through these regions. The filaments can span hundreds of millions of light years. Between them lie great voids, nearly empty regions where very little matter exists. The dark matter filaments act like hidden scaffolding for the visible universe, shaping how galaxies grow and where they go. Yet we still do not know what dark matter is. The structure is there, immense, unseen, and quietly holding the universe together. And even empty space is not truly empty. The vacuum itself has quantum pressure. According to quantum physics, what we call vacuum is a sea of activity. Tiny particle-antiparticle pairs blink into existence and vanish almost immediately. These quantum fluctuations happen all the time, everywhere, creating a kind of restless background to reality itself. This activity creates pressure, known as vacuum energy. On large scales, this may help explain dark energy. Unlike other energy, vacuum energy does not dilute as space grows. It stays constant, stretching space faster. The more nothing you have, the more something it becomes. The quiet force of empty space may be what drives the cosmos apart. The invisible dominates the present, but the past holds its own mysteries. The universe may be older than 13.8 billion years. Most estimates place the age at about 13.8 billion years, but not all methods agree. Some observations of ancient stars suggest they may be older than that estimate allows. These tensions have not been resolved. Could the universe be older? Did we miss something fundamental? In its earliest visible moments, the universe looked very different. The early universe once glowed orange. In the early days after the Big Bang, the universe was a hot, dense plasma glowing with intense light. But as it expanded and cooled, that glow shifted. When the temperature dropped to around 3,000 degrees Kelvin, the first atoms formed, and light could travel freely. At that moment, the universe would have looked orange. Not the blue-black of night we see now, but a soft, warm radiance filling all of space. This light has since been stretched by expansion into the faint microwave glow we detect today. But long ago, there was a time when the entire cosmos glowed orange. As if lit from within, a quiet ember fading into time. Quantum fluctuations shaped all cosmic structure. At the smallest scales, tiny random fluctuations in energy appear and vanish instantly. During inflation, space expanded at unimaginable speed, stretching these fluctuations to cosmic proportions. Those fluctuations became the seeds of structure where galaxies would form. The grand structure of the cosmos may trace back to fleeting random events at the smallest possible scale. Everything born from the trembling of nothing. Ancient sound waves are frozen into the cosmos. In the early universe, pressure and gravity created oscillations in the hot plasma, like sound waves. These left an imprint in matter's density, a frozen echo visible today in galaxy distribution. A preferred distance between galaxy pairs, like a standing wave preserved in space. This is baryon acoustic oscillations, a wave that never fades. But not everything fits neatly into models. The universe contains a mysterious cold spot. In the cosmic microwave background, the faint glow left over from the Big Bang, there is a patch of sky that is unusually cold. Not just a little cooler than its surroundings, but significantly colder and much larger than scientists expected. This cold spot spans hundreds of millions of light years, and its presence does not quite match the smooth randomness we would expect from early universe physics. Some think it may be the imprint of a vast cosmic void. Others wonder if it could hint at something even stranger, like the collision of our universe with another in the very early moments of inflation. No explanation so far fully fits. The cold spot remains one of the most quietly unsettling puzzles in cosmology. Not a screaming anomaly, but a whisper that something about our universe may not be what it seems. The cosmos is still ringing from its earliest moments. In the first fraction of a second after the Big Bang, the universe expanded explosively during inflation. That burst left behind ripples, quantum fluctuations stretched across space. We see them in the cosmic microwave background as temperature variations, and we may one day detect them as primordial gravitational waves. The universe may seem quiet, but it still carries the memory of that first vibration, like a bell still humming long after the strike. There may have been no before the Big Bang. According to general relativity, time itself began with the Big Bang. That moment was the beginning of space and time as we know them. Asking what came before is like asking what is north of the North Pole. Some theories suggest a previous state, but in most models, before the Big Bang is not a place we can visit. The Big Bang was not an explosion in space. It was the beginning of space. The beginning shaped space, and space shaped structure. The universe's large-scale structure resembles a neural network. When astronomers map galaxy positions across enormous distances, a surprising pattern emerges. Galaxies cluster along thread-like filaments, with vast empty regions, cosmic voids, in between. This interconnected web stretches across billions of light years, called the cosmic web. What is eerie is that when you zoom out far enough, this structure looks uncannily like a neural network. Dense nodes of galaxies like neurons, and filaments like axons connecting them. The resemblance is purely structural. The universe is not thinking, but it is quietly beautiful. Galaxies are connected by this vast cosmic web. Over billions of years, dark matter formed enormous filaments stretching across space. Galaxies tend to form and move along these filaments, like beads on a string. Where filaments cross, we find superclusters, enormous knots of galaxies. We cannot see the filaments directly, but we infer them by observing how galaxies cluster and how light bends passing through. The filaments span hundreds of millions of light years and connect vast clusters. They act like hidden scaffolding for the visible universe, shaping how galaxies grow and where they go. Within this web, violence happens quietly. Some galaxies are consumed without leaving visible traces. When a small galaxy comes too close to a larger one, gravity tears it apart. Its stars are pulled into long streams, absorbed into the larger galaxy's halo, eventually blended so thoroughly that the smaller system vanishes from view. We have found remnants around the Milky Way, stellar streams arcing through the sky. Once part of other galaxies, now quiet evidence of galactic cannibalism. Our own galaxy hides much of its mass. The Milky Way has a massive, invisible halo. When we look at images of the Milky Way, we see a glowing spiral, but surrounding this is something vast and mostly invisible: the galactic halo. A huge sphere of diffuse gas and dark matter extending far beyond the visible edge, reaching distances many times greater than the disk. It contains ancient star clusters, stray stars, and vast amounts of unseen mass. Though we cannot see it directly, we infer its presence through star motion and light bending. The Milky Way is just the bright center of something much larger, and we sit inside a local bubble. Earth sits inside a giant bubble of hot gas. If you could see in invisible wavelengths, you would find our solar system inside a vast, glowing bubble of hot gas. The local bubble, stretching hundreds of light years in every direction. This bubble was carved by ancient supernovae, exploding stars that blasted shock waves into surrounding gas, heating and clearing it. Now our solar system drifts quietly through this low-density region, a kind of quiet chamber around us, born from violence long ago. Beyond our local structure lie enormous empty regions. The Boötes void spans 330 million light-years. It is not just a patch with fewer galaxies, it is a vast cosmic void stretching for hundreds of millions of light-years. One of the largest known empty regions in the observable universe. Inside the void, there are very few galaxies, an eerily quiet expanse. These voids are not truly empty. They contain dark matter and some gas, but almost no stars or galaxies. They are the spaces between the cosmic web's filaments. And we may inhabit a similar structure. We may live inside a giant cosmic void. Some researchers believe we may be inside one of these voids right now. A relatively underdense region compared to the average cosmic background. If true, it could help explain certain observations like the expansion rate or patterns in the cosmic microwave background. Living inside a void does not change daily life, but it means what feels like emptiness may be part of a much larger structure. The quiet middle of a cosmic bubble, gently drifting through a web of invisible gravity. Even within voids and emptiness, the universe is never truly quiet. Empty space is filled with quantum fluctuations. In the deepest reaches of space, the universe is never truly empty. Tiny particle pairs blink into existence and vanish almost immediately, creating a restless background to reality. When we picture space as silent and still, that image is only partly true. Beneath the quiet lies a hidden hum of creation and disappearance. And even nothing has a temperature of 2.7 Kelvin. If you travel far from stars, planets, and galaxies into deep intergalactic space, you will find yourself surrounded by what seems like pure emptiness. But even the vacuum has a temperature, about 2.7 Kelvin, just a few degrees above absolute zero. It comes from the cosmic microwave background, the leftover glow from the Big Bang. Now stretched and cooled by billions of years of cosmic expansion, this faint radiation fills the entire universe. No matter where you go, it is there. The quiet thermal signature of the early universe still lingering. And invisible particles pass through everything. Trillions of neutrinos pass through Earth constantly. Right now, trillions of neutrinos are passing through your body. These incredibly light particles are produced by the sun and exploding stars. They barely interact with matter, flying straight through planets without leaving a trace. Other particles strike us from deep space. Cosmic rays strike Earth from deep space. Every second, high-energy particles called cosmic rays hit our planet from the sun and distant parts of the galaxy. Most are deflected by Earth's magnetic field, but some reach the surface, and a few pass through you. These particles remind us that space is alive with motion and invisible messengers from far-off events. Cosmic rays can flip bits in computers. When a high-energy particle strikes computer memory, it can flip a single bit, called a soft error. Spacecraft, airplanes, and ground computers experience these occasional random errors. The invisible rain of cosmic rays continues. The universe's most violent events create the brightest flashes. Magnetar hypernovae are among the brightest explosions ever. There is a rare kind of explosion called a magnetar hypernova, and it may be one of the brightest things the universe can produce. A magnetar is a neutron star with an unimaginably strong magnetic field, trillions of times stronger than Earth's. If a massive star collapses into a magnetar and releases its energy quickly, it can produce a burst of light and energy far more powerful than a typical supernova. These events may be responsible for some long-duration gamma-ray bursts, flashes of high-energy light that travel across the universe and briefly outshine entire galaxies. And gamma-ray bursts are themselves astonishing. Gamma-ray bursts outshine entire galaxies. Gamma-ray bursts are among the most energetic events in the universe. They are brief flashes of high-energy radiation, lasting from milliseconds to several minutes. During that time, they can release more energy than the sun will emit in its entire lifetime. For a few seconds, they can outshine every star in their host galaxy combined. Most are thought to come from the collapse of massive stars or the merger of neutron stars. They occur in distant galaxies, billions of light-years away, but we can detect them from Earth. And some cosmic signals remain mysterious. Fast radio bursts remain unexplained. Astronomers have detected mysterious millisecond-long pulses of radio waves from deep space. These fast radio bursts are incredibly bright, coming from distant galaxies billions of light-years away. Some repeat, others appear once and never again. We do not know what causes them. They are among the most puzzling signals in astronomy. Brief, powerful, and still unexplained. These mysterious signals come from galaxies, and galaxies themselves are strange. Some galaxies glow without visible stars, Astronomers have discovered galaxies that shine but barely contain any stars. These systems are full of gas and dark matter but show little star formation. They are nearly invisible, except in certain wavelengths, faint smudges in deep surveys. Some galaxies are mostly gas and dark matter. Some galaxies contain very few stars, mostly gas and dark matter instead. They may be failed systems that never formed many stars, no fireworks, just quiet gravitational presence. Certain galaxies fire jets millions of light-years long. At the heart of many galaxies lies a supermassive black hole. As matter falls toward it, some gets caught in magnetic fields and blasted outward in narrow, powerful jets, streams of plasma moving near the speed of light. These jets can stretch far beyond the host galaxy, reaching lengths of millions of light-years. We see them glowing in radio wavelengths, forming enormous lobes that mark their reach. The most powerful outflows come from the regions around black holes, where light can barely escape. And some galaxies push material out in different ways. Galactic superwinds can blow stars away. In some galaxies, especially those with active black holes or intense star formation, powerful winds blow out from the center, carrying gas, dust, and even young stars with them. These superwinds can stretch for tens of thousands of light-years, pushing material into intergalactic space. They are driven by radiation, magnetic fields, and explosive energy. Over time, these winds can strip a galaxy of its star-forming gas, leaving it quiet and red. In this way, a galaxy breathes, taking in matter, igniting life, and then exhaling into the void. Not all galaxies are easy to see. Entire galaxies can vanish behind cosmic dust. Even something as massive as a galaxy can be hidden by dust. Thick clouds of interstellar dust obscure the light behind them. When a galaxy lies behind one of these clouds, much of its light is blocked in visible wavelengths. We only see it with infrared, radio, or X-ray light, which can slip through more easily. Astronomers have discovered entire galaxies this way, lurking behind what once seemed like empty sky. Galaxies also move in relation to one another. Galaxies orbit one another. Many live in small groups where they interact and even orbit each other. Our Milky Way has dozens of smaller satellite galaxies. The large and small Magellanic Clouds are the most famous. These companions move around the Milky Way like moons around a planet, slowly tracing long elliptical paths through space. Sometimes larger galaxies pull stars from their companions, forming streams and tidal tails that stretch across millions of light-years. These cosmic dances happen over billions of years, slow and graceful. And our nearest large neighbor is already touching us. The Milky Way and Andromeda halos are already touching. The Andromeda Galaxy is our nearest large galactic neighbor, about 2.5 million light-years away. It is on a slow-motion collision course with the Milky Way. In about 4 billion years, the two galaxies will begin to merge. Interestingly, the outer halos of both galaxies, their vast clouds of hot gas and dark matter, are already overlapping. In a sense, they have begun touching already. The eventual merger is more of a graceful blending than a crash. And galaxies hold unexpected chemistry. The galactic center smells like raspberries and rum. Astronomers studying the chemical composition of a dust cloud near the center of the Milky Way discovered a molecule called ethyl formate. On Earth, it is associated with the flavor of raspberries and the scent of rum. The galactic center does not actually smell. The vacuum of space would not carry scent the way air does. But the presence of these molecules hints at complex organic chemistry unfolding in deep space. Alcohols, sugars, and even amino acid precursors float silently between the stars. Chemistry unfolds between stars, but time itself behaves strangely. Time flows at different rates across the universe. We think of time as steady, a ticking rhythm that flows the same everywhere. But time is deeply linked to gravity, motion, and the shape of space-time. In regions where gravity is strong, time slows down relative to places where gravity is weaker. This has been confirmed by experiments, satellites, and atomic clocks. Near a black hole, time slows dramatically, but even on smaller scales, the effect is real. GPS satellites must correct for relativity. GPS systems depend on precise timing from satellites orbiting Earth. Because those satellites are farther from Earth's gravity and moving at high speeds, time passes differently for them than for us on the surface. Without correcting for relativity, GPS would be off by kilometers per day. And at extreme speeds, time dilation becomes profound. Traveling at 99.9% light speed would age you only months. If you traveled to Alpha Centauri at 99.9% the speed of light, only about 2 months would pass for you. Meanwhile, over 4 years would pass on Earth. This is not science fiction. It is time dilation, a real consequence of traveling near light speed. Space itself also changes during light's journey. Space expands while light travels through it. When we observe light from distant galaxies, we see it as it was long ago, but also stretched by the space it moved through. As the universe expands, so does the distance the light has to travel, and the light itself is stretched. Its wavelength lengthens, shifting toward the red, called cosmological redshift. The universe stretches the signal on its way to us, a silent record of space's steady breathing. Even familiar distances involve time. Sunlight takes 8 minutes to reach Earth. When you feel sunlight on your face, you are experiencing light that left the sun 8 minutes ago. If the sun suddenly vanished, we would not know for 8 minutes. And greater distances require vastly longer journeys. Voyager will take 40,000 years to reach another star. Voyager 1 is in interstellar space, the first human-made object to leave the solar system. But even at its speed, it will take 40,000 years to reach the vicinity of another star. Space is vast, and even our fastest probes move slowly on cosmic scales. And even nearby objects drift. The Moon drifts away from Earth by 3.5 centimeters per year. Every year, the Moon moves a tiny bit farther from Earth, about 3.5 centimeters, roughly the rate at which your fingernails grow. This slow retreat has been happening since the Moon formed around 4.5 billion years ago. Back then, it was much closer, and a day on Earth was just a few hours long. The cause is tidal friction. As the Moon pulls on Earth's oceans and Earth spins beneath them, energy gradually pushes the Moon outward. It keeps slipping away, little by little, as we spin beneath its distant, glowing light. Time flows differently. Space expands, and the universe itself is aging. We live in the universe's stellar springtime. Right now, the universe is filled with stars, burning, forming, exploding. But this is a relatively recent development. For the first few 100 million years after the Big Bang, there were no stars at all. Since then, star formation has risen, peaked, and slowly declined. We now live in what might be called a cosmic spring, a time when new stars still form, but less than before and much more than will come. One day, stars will stop being born. Star formation depends on cold gas, clouds of hydrogen and helium that collapse under gravity. But over time, this fuel becomes scarce, locked up in stars, blown away by supernovae, or heated beyond usefulness. Billions of years from now, galaxies will run out of the material needed to form new stars. The ones that remain will age, burn out, and fade away. First the blue giants, then the suns, then the red dwarfs, until even the slowest burning embers cool into blackness. The universe will not end all at once. It will dim by degrees. The universe may end in heat death. Cosmologists once wondered if the universe would collapse back in on itself. But evidence now suggests a different fate: slow, endless expansion. As galaxies drift farther apart and star formation slows, the night sky will grow darker. Existing stars will burn out one by one. Black holes will evaporate. Matter itself may decay. And the universe will become colder, quieter, and emptier, a state called heat death. It is not a sudden event, but a long, gentle fade over trillions of years. The cosmos will grow still as energy spreads thin and structures dissolve. The far future will be a dark, cold ocean. Trillions of years from now, the universe will look very different. Galaxies will have drifted apart so far that each one will seem alone in the dark. New stars will stop forming. Old stars will burn out. Even the faint glow of white dwarfs will fade. What remains will be cold, scattered remnants, black holes, and the thin echo of ancient light. Eventually, all that remains will be particles moving through empty space, silent, slow, and alone. A vast, dark stillness, a cosmic ocean with no waves, no wind, and no shore. Most of the universe's history has not happened yet. 13.8 billion years sounds long, but if you imagine the entire future, trillions of years ahead, we are still near the beginning. Stars are still forming, galaxies still assembling. Right now, we live in a moment of light. The universe is becoming more transparent. In the early universe, light could not travel freely. The cosmos was filled with a hot plasma that scattered photons constantly. But as it expanded and cooled, electrons combined with nuclei to form neutral atoms, and light could move unhindered. Since then, the universe has continued to grow more transparent. The formation of galaxies and stars added new pockets of light, and as matter spreads out, there is less to block a photon's path. With time, the darkness has become clearer. Space, once glowing and opaque, now lets light pass through almost unimpeded. And perhaps the story has no true end. The universe may recycle through infinite cycles. The Standard Model describes a universe that began with the Big Bang and will continue expanding, possibly forever. But some theories imagine a different story, one where the universe goes through cycles of expansion and collapse. In these models, the universe does not end with a cold fade or final crunch. Instead, it resets. After reaching a certain point, it might bounce, collapsing inward, then rebounding into a new expansion. Each cycle could wipe away old structures, but preserve subtle traces of what came before. These ideas are speculative but intriguing. They suggest the universe may have no true beginning or end, just a rhythm stretched across unimaginable spans of time. One universe giving rise to another, over and over again.